Okay, hello everyone. So thank you for the introduction. This project is called TSDF, so it's all about how to store and process heterogeneous geospatial time series in Python. And it's a project that we got funded as part of an open research data program by ETH domain, so ETH and EPFL. And it's in collaboration with Gionata, which is a colleague from the remote sensing lab at EPFL, and Son and Charlotte from the IT for research team of EPFL, and me, myself, Martí, which I work in the urban and regional planning community, which is called, the acronym in French is SEAT. So, the key motivation of how this project began is when we were dealing with the spatial time series data. So, like it's actually this very example that motivated the project. So imagine we have 1 month of observations from weather stations every 10 minutes, for instance. So there are many ways in which we could represent this information in Python. So, like, this would be the first example, like a pandas data frame in which we have each time step in the index, and we have a multi-column index in the columns that it's basically the station at one level and the variables that we want to measure in the other level. So in this case, for 33 stations and having these 3 variables, this is what the data frame would look like. So this is what we usually call a white data frame. So it's basically a data frame in which we have a unique index, which in this case it's the timestamp, but we do not have repeated entries in the index. And then each variable is, each level of variables can be represented in the columns, but the important part is that we have a unique index. So the pros of this is that since we have a unique index, we can very easily use pandas to perform time series operations like resampling and so on. But the cons is that the time series need to be aligned, and with that I mean each station should have the same resolution or should work for the same periods. Like a station might have a maintenance period in which it has no data and so on. So if this data is very different across stations, we would have a data frame that would be quite sparse with a lot of non-values probably. And we cannot directly add into this data frame attributes about the station. So in this case, a geometry column, for instance, like where's that station located. So this is why we need to think like which alternatives can we use. So this is the more natural alternative is that is widely used in the community. It's a long data frame. So in this case, we would have a multi-index with the stations and the time. And in this case, the main difference with the wide data frame is that we're going to have repeated timestamps in the index. So this is why in this case I'm using a multi-index so that the combinations are unique, but otherwise we could have the stations as a categorical column and the time as a separate column. But at least in this case we have each variable with its dedicated column, and the advantage of this is that we can have an aligned time series. So in like if we go back here, for each station, the time series can be completely different. One could be at 10 minutes, the other one could be at 1 hour resolution. That's not a problem. That's not a problem. So, but the cons is that now the time series operations are not as natural, so we cannot just use a resample with pandas and so on. We would need a group by apply approach. And we could add station attributes, like for instance, geometry column, but we would have many, many, many repeated values, like 1 value for each observation. So it's still not the best idea if you want to add these attributes. So thinking of alternatives, the easiest, the most direct would be without any use of any external library. We could just have a wide time series data frame, for instance, and another data frame or series with the station attributes, and then we would perform joins when needed, filtered by station IDs based on a spatial operation that we do elsewhere. So, like, we could use two objects and perform, like, for instance, these geospatial operations, but we would still need two objects, and we were wondering, like, can we achieve that with only encapsulating the whole thing into one object only? So apparently in the R community that's a bit better managed, and I think that's what inspired this package called xvec that we found, in which it's based on xarray, and in this case we can have two indexes. So that's great. We can have I just transformed that data, so we still have the 33 stations at 10-minute data for 1 month. And I have two indices, one which is the station and one which is the time. So that's the advantage is that the spatial operations, so the time series operations are directly supported by xarray, so that's already there. And the spatial operations are quite easy to perform using xvec. In this case, I can get that's the map of my stations. If I get the location of Lausanne and I add a buffer of 10 kilometers around it, I just use this simple function called query and get the stations that are I get an xvec xarray dataset object with these two stations only. So I can have a single object in which I have the temporal and spatial operations supported. But it has just shortcoming. Well, so this is the pros that I said. Like, I have the efficient operations on both the time index and spatial index that are supported natively. But the shortcoming is that we still require a line time series. So again, we have that same time index. So if each station operates at different resolutions, we would probably still have a lot of NaN values. We would probably still have many periods with empty data for a station that was not active, and so on. Also, there's another issue, it's how to store it to disk. So what the documentation suggests is to use either Pickle or joblib, but they're Python only. And we can use GIS formats, but to that we should transform the data into a wide or long format. So basically, we would have the same pros and cons that we described before. So to wrap it up, we did not find a tool to deal with unaligned time series with reliable disk storage that is like cross-platform, cloud optimized, and that we can add station attributes, or it could be sample, it doesn't have to be meteorological stations, but we cannot add these attributes about the locations for which we have the time series data. So this is the library that we're developing to that end. So it's called TSStore. So to clarify a bit the terms, TSStore is the name of the library, and it has two main features. The first one is a set of objects, so the TS object, TSDF, TSLong, and TSWide objects that encapsulate time series data so that we can organize them, even if they're heterogeneous, we can organize them into Python data frames. And the other part is the storage, which is called the TSStore, like the package. And it's a specification to store the spatial time series data based on Parquet, and if there's geospatial information, GeoParquet as well. So to show a bit the time series encapsulation, so we can have, if we had a TS object that represents the time series, we could easily transform the long data frame into something like this. We have for each station a column named data, and each item is the time series that correspond to that station. In this case, we would have the 3 variables and the same number, these 4,464 observations, But if we had different resolutions, each of these TS objects could have different shapes. So the advantage is that it's quite flexible in this sense. For the stations, they could have different resolutions and periods of no data and so on. And each TS object may be univariate or multivariate, so I could also represent it this way. So I could have a TS object that has only one column, and then my data frame would look like this with a, so I don't know, imagine in one station there has not been rain for a month, so maybe my precipitation object could be an empty TS, but the temperature and water vapor would still have data. So we can support univariate and multivariate objects. So this is it's quite simple, the idea. For each station ID and variable, we can have a time series object. And the whole column would be a TS array, which is a pandas extension data type. And the column itself is a TS array, which this basically means that we have support for basic pandas operations like the null ability to check if any TS is none or not. Also to compare if we wanted to even sort these TS items. So we can do it using this pandas extension interface. And it would be naturally compatible with GeoPandas. So we do not need to repeat the geometry or any other attribute that we want to add to a station in this case. And the second part is the storage. Like I said, it's called TS-store. So basically, when it's a specification to store the time series using Parquet, and when geometries are present using GeoParquet. So if we have 5 years, for instance, of temperature and precipitation data from a number of stations, it generates a folder structure like this. And inside each year folder, we would have Parquet files. And we can have multiple temporal partitioning. So instead of by year, we could have it partitioned by month. Or we could partition differently each variable. Like the structure here, it has the station outside and the variable inside, but we could do it the other way around. We could have a first level with temperatures, and inside there have all the station IDs. So that depends basically on the needs of the user. And the advantage is that the objects are loaded into Apache Arrow, so we have 0 copy conversion to pandas or polars or dask data frames. And for this example, I think maybe I have a notebook here, I hope it's gonna work. Yeah, so what I've been explaining here, it's basically in this notebook. And here I just downloaded the 5 years of data so that we do not have to wait for half an hour. And so this is the 5 years of data that we have. And I first dumped it into a CSV to have some comparison numbers. So now, like I said here, I just give it the name of the base folder that I want. And if I want to have the station IDs first or variables first, in this case, I'm going to have the station IDs first. That's the name of the variables, the station, the time, and which variables I want to store and how I want to partition it. So here, I'm just going to now execute it, and it's going to show the structure. So the TS store, it's dumped in about 7 seconds, and it generates this structure. This is each station ID, has some Parquet metadata, and we have the Parquet files here. And basically, if we compare, it took 200 seconds to write a CSV. It took 7 seconds to write the TS store, and the CSV takes 310 megabytes. And since Parquet has compression, here we're talking about 250 megabytes. And now, we built the TS store, but we could open a TS store that somebody else shared in an S3 server or something. So if we wanted to read the whole thing, so we would just use TS store, open TS long, and give it the base directory. And if we want to read the whole data It's going to take a bit longer than a CSV. Here we see that the CSV was read in 7 seconds. I think this should take about 20 seconds. So if you want to read the whole data, it might not be the best option, but when you have a very large data set and you're only interested in subsets of data, it's what we're going to see now. So if I wanted just to read the temperature instead, in the same openTSLong function, I would just pass the list of variables. In this case, only the temperature. Takes 2 seconds. And the best part would be that I can open a TSDF. So basically, this is going to be loaded lazily. So just build the structure of the data that we have for each station. And whenever I want to read anything, and let's say I just want to read for the station with ID 1, the precipitation data, again, I just use this is just DataFrame. I just get this index and column, and since it's with dask, I use compute, and this is read in 0.3 seconds. So that's basically the main features that we have implemented right now, but it's still a work in progress. The project is due by the end of August. So for instance, what we're working on is to here directly at the geometry column, and the geometry column would also be with GeoParquet here considered. Also, like another example of what we can do, instead of storing, like I said, we can have univariate or multivariate time series. So imagine that I want to group together the temperature and humidity, but have the precipitation separate. I might be interested in this because if I'm in a location that has periods with no rain, the rain files will be compressed a lot with Parquet. So in this case, if I run this and passing this dictionary mapping variables instead of just a list of variables, yeah, so it's going to generate pretty much the same structure instead, but we'll have folders with the sparse data, which is the precipitation. It's going to have the Parquet files, and with the more continuous data. And like again, if I wanted to, I can read them. Well, this had to happen. Oh yeah, of course, if I should change this. So I can just read the more continuous data, or just and it's the temperature, water vapor, or the sparse data, which would just be the precipitation data. And again, like all these zeros, when we write them to disk, would be compressed. And here it's Swiss data. There's rain is quite constant, but if we go to a drier region, I have data from Spain that have had more than 3 months with absolutely no rain. What we can gain in terms of compression is much bigger. So basically, going back to this example, this is basically what we showed on the notebook. And just to wrap up, there might not be the exact same figures, but I ran the notebook before, and it took 133 seconds to write the CSV of 310 megabytes, and to read it, it took about 8 seconds. The TSStore was written in less than 5 seconds, and the file size with snappy compression, it's about 250, and I can use, there's typo here, this is with JZip compression. This is directly supported with Apache. So if we use JZip compression, this is less than 200 megabytes. And again, if we want to read the whole thing, it doesn't make sense. It's going to be faster with the CSV, but whenever we're interested in just, for instance, a single variable, it's much faster, and in the CSV we're always going to have to read everything. And if we're going to read like a single variable in a single station, it takes 0.03 seconds. So just a bit of the roadmap, because like I said, the project is due by the end of August. We're working on having GeoPandas and GeoParquet support. And time filters, I just showed we can filter by variable when we're reading data, but if we want to filter and just read a specific period of time, that's also going to be supported. And the last work package is to implement more advanced time series and spatial operations. So directly implement group by, regularization, resampling, and rolling window, and so on. And that's it. Thank you very much. It's just the links of the labs that are involved.
Okay, thank you, Marty. You are very good in time. Are you sure you don't have any more demos?
No, I just took some extra time in case something didn't work.
That gives us plenty of time for questions. So if you have any questions, please raise your hands. One question for me. Do the time series data types, are they allowed to have different shapes, or do they have to be like the same shape?
Yeah, no, that's the main point. They can have any shape. Like they can be, they can have different resolutions. They can have different numbers of variables and so on. That's kind of the whole point.
Okay, thank you.
Thanks. So sounds really interesting. I was just wondering, in your time comparison, so is this reading the whole data and the fact that it takes so long just related to decompressing it? Or like, did you try this without applying compression?
We didn't. I mean, technically we could just instead of using Parquet files, we could just use CSV files, just have the hierarchical structure, but use CSV files. But I think it takes longer because it has to compile the list of files to be read more, because the reading time of a single file is very fast. It's just the part of compression might be a part of what takes long, but I think what really takes long is to compile the list of files that need to be read. So I mean, this doesn't make sense for very small data sets, but when you have a large, if we wanted to have like years and years of data, and this is just a tiny example of, there are 33 stations in the canton of Vaud in Switzerland, but if you had a whole country and you have different station providers and so on, at that point it makes a lot of sense to not have a CSV or...
Hi, I have a question about partitioning of the Parquet files. How do you partition them, and can you optimize maybe the partitioning so that you know, there's not hundreds of files created, but just maybe 5 if you have limited data, or yeah. So basically, we support a series of strings that I think are dictated by. Depends on if you're using pandas or arrow and so on, but it's like year, month, and just time groups. But I think what the thing is that each Parquet file should be big. So partitioning, probably if you don't have a lot of data, partitioning by month doesn't make sense. So we just have these time strings, and you can group by year or month, or a list of strings that are accepted by pandas and polars and other specifications. But you need a minimum size of a data set for each partition to make sense. So is it something that you choose beforehand? Or can you adjust it?
No, you can adjust it. It's just a parameter when you just put the 2_ts store. It's just like one of the parameters is partitioning, and in this case I wrote year, but it can be any time partition that you want.
More questions? Okay.
Thank you. It looks a very nice format, and tidy way to have the time series.
Thank you.
So my question is, if I want to slice specific stations, because for example I want to divide for a specific value, or subtract a specific value, an offset, for example, that I know that there is an error, how would I do that when I have a data frame and the time series stored like that?
You mean values of the measured data or the station locations?
Of the measured data.
So like selecting...
let's say station 1, 10, and 15, I need to subtract from all the values of the time series the value 10. How would I do that?
So I think this is one of the things that we're gonna have to implement in this second package, where we have the group by applies and regularize and resampling and rolling window operations. I think this should be more of kind of a group by apply kind of operation, maybe wrapped into a nicer interface. But the filters that we implement kind of at read time, it's the variables or stations that you want to read, and the time filters if you're just interested in certain, so that we only open the partitions required. But then, yeah, I think it's not implemented yet, but I think it should be more like a kind of group by, or maybe if we realize that there's a nicer interface to achieve that, we will do it. We will keep that in mind. But beforehand, I think it should be kind of a group by apply
Got it. Thank you.
kind of operation.
More questions? I have one more question. Should we think about the T-store as a columnar or row-oriented format? What is the right conceptual model?
So I mean, it's the backend, it's Parquet, and the memory model, it's Apache Arrow, so we are not changing any of that. So, and we really rely on their implementation in that sense.
Okay, but the time series data types, they are stored in cells, so to say, so in the data frame inside.
So each TS object, it's basically an Apache Arrow memory representation that then you can transform into a pandas or polars or dask data frame. And you could, like, it's just an abstraction over it. I think you could have it in a columnar or row format. Depends, but I don't think it. I think we are always going to have rows on the index in the inner data model. If you have pandas or polars, I don't think any libraries have that differently.
Okay, thanks. One last chance for question.
This is possible to use this one for stations where for every station there are different time intervals.
Yes.
For one station. For example, we have, I work often with data from logging stations where the time scales for the logging station is different. It's not always every 10 minutes. It differ in one station. And you have 10 stations, and they differ, and the station only differ.
Yes, that's perfectly possible because, like, for each station, you're going to have a TS object, and this TS object, you can have any index that you want. The issue comes, like, if that time series it's irregular, it's fine. The issue is that if you put many irregular time series together, if you have 10 stations that have this kind of pattern, you would end with a very sparse array with a lot of non-values. So it would perfectly work. It would be a great use case, actually, to have every station with an irregular time series. So you would have, like, a dedicated irregular data frame for each station. Because I work with cities and weather stations that are like people that have a weather station home, and they're more irregular than the official ones. And I also kind of have this, so this was one of the motivations as well.
Okay, last question.
Would it be possible to deal with real-time data or live data, or you have to re-index the entire? I mean, what if you have some streaming data and?
So the only issue is that the Parquet files are immutable. So if you have, like, depends on how you partition the data. You would have to basically read that Parquet file, load it into pandas or polars or something, add the data and rewrite it. So probably depends on the resolution and how you partition your data. I think if you have to read a whole file and delete it and rewrite it, it probably wouldn't make sense. But if you can partition it in a way that when you stream it, it goes directly into a different Parquet file, it could probably work. But the data should be quite big for it to make sense. Otherwise, the overheads would... but depending on the data size, it could make sense.
Okay, great. Thanks, Martí.